but let's thank the speaker one more time, and we'll move on to the next.
All right, is this working? Perfect, okay. So today I'm gonna present some work with my wonderful co-authors from Carnegie Mellon on the current debate over differential privacy at the US Census Bureau. And my goal today is to try and sort of expand this debate, which I'll tell you a little bit about, by using differential privacy to talk about some larger existing equity issues with the way that policy deals with or really doesn't deal with statistical uncertainty. So you may have heard of differential privacy. Differential privacy basically gives us a formal bound on how much an attacker might learn about individual respondents from statistics published about them. And it's a very popular formal standard for privacy. And recently it's been hitting the big stage. Perhaps most prominently, it was used in the 2020 decennial census. But over the past few years, there have been lots of political and legal fights over those new privacy methods. Including concerns about impact on redistricting and other democratic processes like voting rights. And the issues that people are raising mostly have to do with the way that we achieve differential privacy, which is by adding statistical uncertainty or really just noise to statistics before they're published. And so typically studies on differential privacy like these will treat the census before differential privacy as sort of a ground truth, and then see what adding noise does to certain applications of interest. The focus of our work is this. If we think about all of the different kinds of statistical uncertainty affecting census data, differential privacy is really just the tip of the iceberg. If you've ever worked with census data, you know that the margins of error can be shockingly large. And most of the debates about differential privacy overlook all these other forms of statistical uncertainty, sampling error, measurement error, stuff like that. And what I'm going to show you today doesn't even include the unquantifiable forms or unquantified so far forms of statistical uncertainty whose impact we don't know. Most notably, previous privacy protections like swapping or top coding, where the census doesn't disclose exactly how they work. So there are these sort of hidden distortions in the published statistics. So to try and illustrate this idea, we're going to focus on a very quantifiable setting. So more than $1.5 trillion of the 2017 federal budget were allocated using census data. And specifically, we're going to focus on one grant program in particular, Title I, which distributes education funding and could possibly be affected by a future or formal privacy standard. So how is Title I being impacted by statistical uncertainty? To give you sort of a preview of the $12 billion in Title I grants that we looked at, some school districts lose over $1 billion and other school districts gain over $1 billion in 2021 because of misallocations due to just data error. And crucially, when we add differential privacy on top of that, that number only goes up a little bit. So an extra $50 million lost if we add a stronger privacy guarantee, and less than $1 million in additional misallocation if we add a weaker privacy guarantee. So it's clear that there's this serious existing issue with formula funding. That's that purple bar, even before we start to talk about adding extra noise. And what's worse, Title I distributes the impacts of uncertainty unequally across demographic groups. So the people that these policies are designed to help and who have historical reasons to care a lot about privacy are also the most adversely impacted by statistical uncertainty. The upside to this sort of bleak picture is that if we focus on this larger problem of statistical uncertainty instead of just that marginal change, we can see some simple reforms that we might make to get Title I working better for marginalized groups and still have those strong privacy protections. So that's what I'm going to try and work towards today. So to get those numbers, the first thing we did was replicate the Title I allocation process that's actually used by the Department of Education. This allocation process relies on basically a special tabulation of poverty estimates from the Census Bureau. That's on the right there. And of the 13,000 school districts across the 50 states included in this process, only some of them are going to qualify for each of those different grant types. So for example, for the basic grants, you have to have at least 10 children in poverty to qualify for funding. And then for each of those qualifying districts, we're going to use a formula to calculate the entitlement amount. which is basically a weighted sum of the eligible children, and the weights that we use depend on which grant type we're talking about. So we're going to use these entitlements as a baseline for our analysis, but in practice, we actually have to iteratively recalculate those entitlements and until these two like post-formula provisions are met. And I'll talk about those a little bit more later. So we're actually building on some other studies on privacy utility trade-offs in this context. But for our study, we're going to try and add some more policy elements to make it a little bit more realistic. So we're going to use that full allocation formula, including the first 3 grant types there. And we're also going to use the official 2019 census poverty estimates that the Department of Education actually used in 2021. So now that we've replicated sort of the Title I process, to add uncertainty into the picture, the first thing we're going to do is add data error. And we're going to simulate basically the published census variance estimates for this data product to sort of draw a normal distribution from the sort of sampling distribution for these data. And we can think about these observations as like what we might get in an alternate world where the estimation process went differently. And then the next thing we'll do is on top of that, we'll add privacy. Now, this data product doesn't have a formal privacy guarantee yet. It's actually based primarily on the American Community Survey, so the census is still like in the process of deciding what to do with it. And to sort of approximate like an upper bound on what might happen, we're going to use one of the simplest ways to get differential privacy, which is the Laplace mechanism. Our privacy guarantee is going to be strong when that epsilon parameter is low and the amount of noise added is high. So low epsilon means strong privacy. And generally this privacy noise, so the second step, is much smaller than the data error from the first step, at least for this granularity, right? They're only equal in like the very smallest districts, and that'll come up later. And then finally, we'll run these noised counterfactual estimates through the allocation process. And for now, I'm going to refer to the difference between our simulated allocations and the official allocations as a misallocation. So yeah, let's look at the results. You've already seen this figure, which is just the average sum of all of the negative misallocations or funding losses across the entire nation, and averaged over 1,000 runs of our simulation. And now I want to sort of dive into who is being impacted by the way that Title I is distributing uncertainty. And for now, we're just going to focus on results for that stronger privacy setting that we looked at. So this is sort of an upper bound on what the impact might be privacy-wise. So this is a map of the geographic distribution of misallocation due to just data error. So this is just the simulated observation after we added that normal noise, minus the official allocation, no privacy noise yet. And we added a cube root transformation to make these differences more visible. Here we're just looking at the expected misallocation. So this is the average for every district over 1,000 runs of the simulation. Districts that are in blue expect to gain money. Districts that are in red expect to lose money. And districts that are sort of whited out are statistically insignificant at 90% confidence. So why are we seeing this particular pattern of outcomes? One thing that's happening is that the districts with only a very few children in poverty, they don't have much to lose, right? So they're receiving like $0 or very few dollars. And then when we add noise, they qualify for new grants. They have large proportional increases in funding. And so they make pretty large gains compared to the larger districts, which then, because it's a zero-sum game, have to pay a small tax to compensate for those gains in the small districts. And one thing to note is that this is the trend in the expected outcomes. But for the funding volatility, it's the opposite trend, right? So if you or these blue districts that are expecting to gain on average will also have worst case outcomes, right? Because the noise is proportionally higher for them. So the two fundamental mechanisms going on here, because what we care about is children in poverty, is the population size, so how many people are in the district, and then also what the poverty rate in the district is too. So you can already see that the poverty rate, which is what we really care about with these grants, is determining how the uncertainty is distributed. So what about privacy? This map shows the marginal change in misallocation due to privacy noise. This is like the additional effect of privacy on top of data error. Remember that the marginal difference here is relatively small. So these effects of privacy noise might actually be in the opposite direction of data error, like Maine switches from red to blue. And so, but we can still see even clearer patterns here geographically. And that's because unlike the data error, differential privacy is population invariant, right? So the data error is sort of proportional to your population size, but the privacy noise is the same for everyone. So those disparities get exaggerated. So what do these patterns mean for demographic groups, right? It depends on where you live and your poverty rate. The first thing to notice is these two charts show the basically the race-weighted misallocation for census single race and single ethnicity groups. This is like how much of the burden of misallocation is the average student in these groups bearing across the entire nation. So the first thing to notice with these charts is that while white students gain, that's these two red boxes here, marginalized groups in general tend to lose out. And that's even more exaggerated for like geographically concentrated groups, like tribal groupings, which actually just happen to gain here because they're in more rural districts sometimes. So thinking back to the map from earlier, the groups that tend to live in the denser districts with higher rates of poverty are losing out, while the groups in the sparser districts with the lower rates of poverty are gaining. Just sort of the opposite of what we might want. And the impact of privacy on top of this also depends on those same factors. So for example, the impact of privacy is very large for Black students, but it's negligible for Japanese Americans. So it varies across groups. Now, one thing to note is that this is the stronger privacy setting. If we sort of make our privacy guarantee weaker, then these marginal differences will disappear. So those green bars show just data error, and then this black outline shows the additional impact due to privacy. And it's going to be dashed if that additional impact is negligible. So you can see for the Black or African American students, it's a very large gain. For the Japanese American students, it's very small. So we might ask, is this sort of an inevitable situation, or is there something that we could do about it? One thing we could do is we could create an uncertainty grant, which is basically a grant we distribute to all of the districts that we think are going to lose funding, so that they don't expect to lose any funding on average. And taking our assumptions, we could pay just $107 million in total to compensate every district that expects to lose money due to just data error. And then if we additionally want to compensate for privacy error, we can add either 41 million for that stronger privacy setting or like 1.7 million for that weaker privacy setting. If we also care about like funding volatility, so the worst case scenario, we could pay like $4.7 billion. There's like 25% of the whole budget, in addition to compensate for like that 95th% worst case outcome for each district. The other thing we could do is just like put more money into the budget overall. That's like half as efficient based on our results. And that's because the disparities in the allocation mechanism are still there, right? So just paying more money won't fix the underlying problem. So for example, I mentioned those post-formula provisions earlier. Hold harmless is one of those. It's shown in purple. And basically hold harmless limits the amount that a district might lose from year to year. So it sort of stabilizes funding. But it also keeps the marginally wealthy districts from losing funding over time. And so you get these really big disparities compared to the baseline, which is in black. And so one thing we could do is make some policy changes that sort of reduce those kinds of disparities. Like, for example, if we use a moving average or a multi-year average instead of those single year estimates. So if we use like 2015 to 2017 averaged instead of just 2017, we can drastically reduce disparities and still get some of those stability effects that hold harmless gives us. So there are some things that we can do to change the allocation mechanism that would help with statistical uncertainty. Now, the analysis that I've just showed you is sort of only partway down the rabbit hole. I mean, I mentioned that we only looked at the quantified statistical uncertainty. The effects of data error could be even larger. There are also these like systematic undercounts that are hard to measure and also hard to estimate in like this sort of analysis, including from like post-processing. Sometimes differential privacy requires post-processing. So that complicates the picture. So here we sort of took an upper bound approach, like what's the worst case scenario for privacy. And the other thing is we can only really say how the funds are distributed. We don't actually know how they're being used within school districts. So that's another complication. But there are some clear takeaways, I think. If we look at differential privacy on the margin of existing data error, the picture is going to look a lot different. So in particular, we see that this $1.5 trillion in census-guided funding really needs to reckon with statistical uncertainty in general. And that could actually help us solve some of our differential privacy problems. I think in the current legislation, there's like one provision for uncertainty where if you live in a district with less than 20,000 students, or less than 20,000 people, then you can appeal your count. But it's not clear like who's doing that, if it's gamified. Like, maybe you would just appeal your count all the time to like the highest you could possibly get it. So I don't know if that's really helping. And there are lots of other programs that use very similar mechanisms that are also census guided. So we can expect this to maybe this would show up in other places too. But there's sort of a hopeful takeaway here, which is like, we think about this differential privacy debate and we're worried about adding extra noise. We should also ask like, how is our policy currently dealing with statistical uncertainty? Because there could be easy ways to do a better job with our data-driven policy that would make it easier to also have those privacy protections and also get the policy to work better for marginalized groups. So that's what I want you to sort of walk away with today. All right, thank you.
Great. So we have time for one, maybe two questions. I know there's a lot to unpack. I had a question. So at one point you said that there's. Oh. Hello.
Yeah.
At one point you'd said that there is a difference for students who live in larger districts versus smaller districts after differential privacy. Could you explain why that is?
Right. So remember that for both kinds of statistical uncertainty, if you have very few children in poverty, you have a lot to gain. If you have more, you have to sort of pay for those gains with a tax, right? And so the number of children in poverty is both dependent on the poverty rate and also just the size of the district, right? Like if I live in a huge, like if I live in San Francisco, which is like sometimes a really big district, and we don't even know how to break that up, then there are lots of students there. So even if the rate of poverty is really low, there's still going to be more than there are in like Nebraska, right? So actually the way that states draw their districts in terms of how large they are population-wise determines some of these things. So you'll see state patterns like in the South in particular for differential privacy, where the amount of noise is constant and you can see the disparities best. In the South, they draw larger districts than they do in like the Northwest. So you'll notice a big disparity there. Yeah.
Yeah, thanks so much for your talk. I'm wondering, so if such a system were implemented in practice, how would you'd have to audit, right? Because you don't have the actual ground truth true population. So like, how do you know when you're distributing funds like these to districts that expect to lose funding due to privacy estimation error or due to actual changes in the underlying demographic?
Yeah, I don't think it's practically or politically sustainable to like make an argument for, first of all, that kind of statistical sophistication, I don't think you could put into Title I to like, say, okay, we're going to make all these assumptions. And then if they hold up, then this is how much you expect to lose. So I'll give you that exact amount. So maybe the worst case funding is more defendable, but it's also $4.7 billion compared to like $140 million. Which is why I think the reforms are a little bit better, right? Because people can maybe grasp an average better than they can, this like complicated. We ran a simulation 1,000 times. Maybe there's a better way to do it if you are the Census Bureau. Maybe the Census Bureau can like make better uncertainty estimates for this product, and if they do that, we can be a little bit more certain. But yeah, it's difficult.